computer engineering has been mostly viewed as a hardware discipline. Most people, if you ask a high school graduate whether they whether they think about computer engineering as a software or hardware, they will have no clue, and they say, oh, hardware. And then if they want to do software, they go to computer science. And what I would like to argue about is, programming is quickly becoming an engineering discipline. And so this is going to be a very interesting and exciting opportunity for computer engineering researchers and educators to begin to think about the future of computer engineering. So you probably have already seen this many, many times, and several previous speakers also mentioned this. The only way to grow application performance in the future is parallelism. And even in Mark's talk, he just walked in, that when he mentioned that to increase the energy efficiency and so on. But if you look at the kind of things he did to drop down that power, consumption, there was a huge amount of data parallelism that he had to use in order to drop down that the consumption. So what we're seeing is the libraries, the algorithms, and the programming tools are all going to have to go through a major transition in the next few years. And you should ask at this point, why is this different from what people have been doing with HPC in the past 30 years? And the answer is, truthfully speaking, the HPC revolution, parallelism development did not really touch the node level much at all. And within the node, the fundamental libraries and algorithms were still sequential, okay? And a lot of the advancement actually had to do with weak scaling rather than strong scaling. And we're just working on bigger data sets and partition the data sets, and then use the sequential algorithms in the nodes to implement most of these systems. But in terms of the moving forward, we're not going to have that luxury. We're going to have to take care of both weak scaling and strong scaling. And all the node libraries and so on are going through fairly rigorous revision. And so I'm going to talk about the engineering aspect of these things. Why it's going to take very, very strong engineering discipline to be able to handle this challenge. David showed a slide, and I think someone else also showed a slide in terms of these libraries. If you look at the landscape, and a lot of people will say programming CPUs is a lot easier than programming GPUs. And the truth of the matter is they're both difficult if you want to get performance out of them. Okay, they're both very difficult. However, the CPU library has advanced in the past 15 years or so. Since the introduction of SSE and so on, there has been a very strong development in the CPU world. And Intel honestly did a very, very good job with MKL. And I'm going to show you some result from MKL measurement. It's, some of these libraries took a long time to develop. And once the libraries exist, it does make the programming job much, much easier. And if you look at the GPU computing libraries today, some of the libraries are in place, but some of the libraries are still missing. Like Magma and CULA on David's list, they still need they need more scalable solvers. And for graph algorithms, we still need to have graph partitioning tools, kernels running in parallel. And for unstructured grid algorithms, we need to have 3D volume mesh generation. And these things are still being done in CPUs and mostly in sequential way. So we're going to need to figure out how we can push these harder library components and so on into parallel form, and so that we can make the programming job a lot easier. So there are really 4 different levels of difficulties. There are lots of grad students here. So when you think about parallel computing, and if you want to do some algorithm work, if you want to do some kind of framework work, make sure that you understand which challenge you're going to be plunging into. The first type of challenge is what I call the fundamental challenges. There are computations with no known scalable parallel form, period. If you take shortest path with the Lonnie triangulation and so on, and these algorithms, there's just no known scalable form. And if you do a thesis and actually come up with a truly scalable form in one of these problems, you're probably going to end up with some big prize at some point, okay? And that's a really, really good goal to shoot for, but you also need to be prepared that you may fail, right? The second one is the data distributions that cause, there are data distributions in real-world applications that cause catastrophic load imbalancing problems. And free-form graphs and MRI spiral scan that David was showing, when the data is sufficiently non-uniformly distributed, it can defeat any kind of parallel computing, okay? So we have various levels of techniques to cope with the problem, but I don't think we have real solution to those problems in a general way. The third one is the computations that have little data reuse. For example, matrix vector multiplication. The matrix part is just not reused. So in order to reuse the vector part, you need to have extremely large on-chip resource to be able to tap into that kind of reuse. So that's why when people look at conjugate gradient solvers and so on today, in order to reduce the memory bandwidth requirement and improve the execution rate for parallel computing, most of these people are no longer using matrix vector multiplication as the fundamental step. Most of these people are actually looking into numerical methods that allow them to do more than just a multiplication, but a polynomial evaluation in each time step so that they can reuse data. Unfortunately, with that kind of reformulation, there is going to be fundamental shift in terms of numerical properties. And what Jim Demo's group, for example, would demonstrate for some of the QR solvers, iterative QR solvers, you can actually get more numerical stability out of the algorithms that use polynomials rather than matrix vector multiplication. However, it's different. So some of the applications developers are extremely hesitant in using those libraries because the results do not match the old results. And there's going to be a lot of work needed to be able to, to introduce these newer formulation into the libraries. And then the fourth challenge is the easiest one. There are algorithms with sufficient data reuse and sufficient locality that if you work at it hard, you can actually get them to work in a scalable way. However, even in those cases, we're not quite there yet in terms of portability across different hardware, and even in the engineering process of putting together a truly scalable kernel for those kind of computation. I'm going to take you through one just to give you a kind of a concrete feeling of how it looks like in reality today. So one thing that I want to, I do want to say before I get into the details is that I'm going to use GPU computing as an example. However, I would like to say that whether you're going to be running the code on a CPU or GPU, the whole engineering process is going to be scalability, and it's going to be about regularization and locality. And in any real world cases where I see massive amount of parallelism, when I see a system that needs to scale to a very large level, there's always a need for regularization and locality. So I'm showing, some military, kind of picture where the large fleets or the army, movement, and then the traffic system, the wedding. There's a big wedding with 1,000 people, and try not to order your steak in a wedding to be medium rare plus a little bit. Do not try to specialize any of that. It's all about regularization and how they can serve you dishes just from the kitchen and in a very regular form. Okay, nobody should ask for any kind of regularization. The corn picture is taken a quarter-mile away from my house. People in Illinois is very, very good with this kind of activity. And then iPod factory. If you want to produce a lot of high-tech devices, you need to be able to produce those devices in very regular and very localized way. So the facility doesn't look high tech at all, but the devices that come out of it can be extremely large volume and high tech. So there are three things that need to be overcome whenever we need to produce a scalable parallel algorithm. The first one is we need to make sure that there's not conflicts in updating critical data structures, so that that we can avoid the serialization. And the second one is oversubscription to global memory bandwidth. For any computation in the future, we're going to only have less and less global memory bandwidth rather than more. And the third one is load imbalance. We need to make sure that the data we can manage the data distribution and layout and so on, so that we can produce a balanced workload for all the computing units. So at this point, we know that there are 8 categories of techniques that people have been using very effectively, whether they're using the techniques for GPU computing, or they're using some of these for SSE type of programming on the CPUs and multi-core. And these techniques actually deal with various forms of problems in the scalability. Data structure contention, DRAM bandwidth, on-chip memory locality, computational efficiency, load imbalance, and CPU-GPU leverage. How you can actually keep all the different devices busy and get performance out of it. So let me take you through a simple, at least seemingly simple example, a tri-diagonal linear solver. And this is one of the easiest linear solvers in the linear solver category. It's a very important core of science and engineering computation. This is, it's used extensively in computer graphics, fluid dynamics, derivative pricing, iterative solver preconditioners, and multi-grid methods and finite difference PDE solvers. The system looks pretty simple. Essentially, you have a system of linear equations, and every equation will have 2 or 3 variables, and they are actually, all the equations, once you form the matrix form, are either the main diagonal or the upper diagonal or the lower diagonal. So then you have a bunch of right-hand side values that the linear system equations need to match. This particular computation is very, very straightforward for sequential algorithm. And it's well known that you can do a what we call the Thomas algorithm, where you can do a forward reduction pass, where the first, if you look at the picture here, we can eliminate A2 by just normalizing B1 and A2 so that we can subtract the first equation from the second equation and eliminate A2 out of that equation. And then B2 and C2 will become new values, and D will become new value, but that's okay, right? So now you end up with 2 variables in the second equation. You do the same thing for the next one, the next one, the next one. In the end, you started with 2, so you end up with 1. And that gives you the solution right there, right? And then you substitute back. It's extremely efficient because it's a linear algorithm, okay? And so, this particular, style of implementation has been used in libraries for years. When you start to think about parallelism, things get a little bit more complicated. But people have already thought about this, so it's not too bad. In general, they fall into what we call the cyclic reduction kind of situation. Remember that if you want to use Thomas algorithm, you need to have a sequential forward and backward path, which is a little bit problematic when you try to introduce parallelism. So one way to look at this is to say, we can reduce the problem. So we can actually use the odd-even neighbors. Okay, so let's say the 2 even neighbors to eliminate the odd variables, or the odd neighbors to eliminate even variables from the equations. So I'm showing you a simple example here where we can use the first and the third one together to get rid of the odd variables from the middle one. And you say, oh, but you just introduced another variable into it, right? That's okay, because now we actually reduce the problem into either odd or even form, so that we can actually split up the problem and have a smaller problem of all the odd variables and smaller problem of all the even variables. So this is a typical trick of using reduction, reduction or recursive methods to partition your problem so that you can do a divide and conquer, right? So intuitively, this is not too bad. And it's actually quite efficient. It's slightly more expensive in terms of complexity. You start to have n log n versus n. But if you can enable enough parallelism, you can make up for the log n and get more speed. So this particular method is essentially the base of most of the parallel algorithms that deal with tri-diagonal solvers. There's a slight problem, and this is usually where all the engineering efforts can come into parallel programming. The problem is there is a very low compute to memory access ratio in that in a straightforward implementation, because every time you go and fetch one of the coefficients, you do a multiplication or you do a subtraction, but it's for every operand you fetch is not a whole lot of operation you can do. So if you do a straightforward parallel implementation, the compute to memory access ratio is about 1. Whereas in most of the modern computing devices, in order to get anywhere close to the peak speed, you need to have about 14. And the ratio is actually creeping up in the past generations. So you will need to use some kind of tiling to coordinate the parallel activities so that they all consume some common input operands. So you fetch a common input operand, and you do something with that common input operand among the parallel devices. And this is standard tiling. And in the real world, it's carpooling, okay? So for those of you who have seen the U.S. freeway traffic pattern, in the traffic hour, there's a carpool line, and say if you have 2 or 3 more people in a car, then you can you can go through the carpool lane. And here it's exactly the same thing. Every time you go to memory, you fetch the data for 2, 3 of your commuters, and then you can use the data and save the bandwidth. So there's another issue with the algorithm, which is the latency to parallelism. Remember, we're doing this reduction. We're doing this recursive process to partition the matrix. So it does take a little bit of time for us to build up enough parallelism to be able to to actually get to the real parallel execution mode. And this allows M-DOS law to creep in. Okay, so now you start to have a portion of your execution time in a enough sequential mode that can eat into your scalability. So data access tiling is conceptually a fairly simple method. You have these threads. Each thread will be accessing multiple data input elements on the upper left-hand side. So you're putting a little bit of synchronization and make sure that these threads make progress roughly along with each other so that you can control the consumption of their input operands. Okay, so it's not bad, so then once you control the consumption pattern, you can control the amount of data that needs to be on the on-chip memory, and then you can make sure that all the parallel activities consume that focused portion of the data before they move on. So you invariably will see some barrier synchronization and so on in the implementation. So let's take a look at the engineering process of tiling. So for this particular one, the tiling algorithm is actually a little bit tricky. The reason is, remember, this whole computation came from this, going from the upper corner, and then you need to use this, the odd neighbors to eliminate the variables for the even, right? So when you have a tile that you want to focus, you invariably will start to see some data that you need to bring in from your neighbors, right? So this is a classic problem of halo cells or ghost cells or skirt cells, whatever people tell them. It's really just information that you need to bring from your neighbor's input pool into your own tile. And also for the computation, once you start to partition your matrix into more and more, you start to need to have intermediate results from your neighbors, so that you can further partition the smaller ones, right? And that propagates very fast. If you want to be able to generate 2 to the k matrices, then you need to have 2 to the k neighbors to feed into your process. So this has traditionally limited the scalability of tiled algorithms for tridiagonal solver. Okay. This year, some of my students came up with a sliding window tiled PCR. Essentially what it does is it still gives you the tiled execution. However, within the tiled execution, you actually use a sliding window to bring in a tile. In fact, it brings in 3 tiles at a time, and then you start to slide. And with the sliding, we can actually eliminate the overhead of fetching the ghost cells and produce enough scalability into the algorithm. And this particular design has heavily engineered. If you look at the way it was designed, there was a very careful analysis of the access patterns and figuring out when to sequentialize things and when to leave things in parallel so that we can actually bring the data in the most efficient way. And unfortunately, this particular style of tiling would enforce some sequentiality across the tiles, right? So then there's a remedy to it. You can actually start another rolling window, let's say halfway in your matrix, but you need to actually do a little bit redundant calculation in order to get that to work. So I hope what I'm making very clear here is that a very simple algorithm problem in the sequential world translates into a fairly complex engineering problem when you try to produce a scalable parallel algorithm. Well, I'm not talking about engineering problems that you need to work on in order to get to squeeze out the last bit of performance out of a particular piece of hardware. I'm talking about engineering an algorithm so that you can work all the techniques that you need in order to make use of any arbitrary on-chip memory, data size, and bandwidth ratios, and so on, in order for your algorithm to be scalable in the future generations of the hardware. So if you look at the execution, it's actually quite interesting. We use a Intel quad-core i7 975 processor plus an NVIDIA GTX 480, and we compared this particular algorithm with the MKL, the Intel Math Kernel Library, implementation. So this figure, the left-hand side of the figure, shows what I was saying about weak scaling. So there are quite a few applications that solve multiple of these tridiagonal systems at the same time. So there are problems where they will give you more than one of these linear systems to solve. So I'm showing an example with 16 of these systems. So if you use MKL today, MKL will do multi-threaded execution on those 16 systems. And you can actually get pretty good performance. The middle curve is the 16-thread implementation. So it does give you very nice speed up. And it also scales pretty well. The GPU implementation down here gives you further strong scaling beyond the 16. Okay? But if you look at a single large system, which is the case for a lot of the financial pricing, the option pricing applications, then the single large system actually does not scale on MKL because of what I said. Traditionally, the HPC community did not really do a strong scaling of a single system solution. Whereas this particular solution allows you to do a strong scaling and speed up the execution of a single system solution. going back to, to a couple other problems, I'm not going to be able to use 40 minutes to really talk about all the engineering problems that we're seeing in parallel algorithms. But one of the things I do want to emphasize is that most of the engineering work is really not about parallelism. It's not really about algorithm per se. It's about data. It's about somehow massaging your data into a form that's amenable for parallel computing, okay? And that's really where the engineering is. So let me just use this quick example. It's a sparse data for MRI scan, and this is actually the real plot of that distribution. So you can see that near the middle of the plot, that's where most of the data samples are, and this allows the MRI machines to get much higher resolution and much bigger pictures without scaling up the samples. So this is sometimes called compressed sensing in some in some disciplines and so on. So what I'm going to use is not what David showed. What David showed was using this particular kind of scan technique, but look for sodium. However, there are also a lot of people who are still using this kind of scanning for hydrogen, for looking at water molecules, but just to get higher resolution and bigger picture. So I'm going to use the gridding path that David used across that picture that he showed, but show you some interesting engineering that you need to do in order to make that particular process scalable. The first reaction that anyone who does this kind of processing is going to say, well, I'm going to parallelize this in a very straightforward way. I'm going to have each thread to process a chunk of my input. And then I'm going to let each thread take the input and go and affect the output points that that contribute to the output points. However, in that approach, because inputs can contribute to overlapping output points, you need to have locking or some kind of atomic operation or some kind of synchronization. So I assume that you're going to be using a atomic operation. And this particular process is very slow for large-scale parallel machines. But as David mentioned, for Fermi GPU, because the atomic operation can now operate in the on-chip cache, this method is actually not terribly slow. It's actually reasonably fast. You can actually get a little bit speed up out of this method. However, if you want to have a scalable method, you're not going to be using atomic operations. You're going to try to avoid atomic operation as much as possible. So a general technique that gets you into that is input binning. It's essentially a spatial sorting technique for data. Again, what I was mentioning. It's not about computation. It's really about data, how you can massage your data into a form that is amenable for scalable calculation. So, I'm using up probably a little bit too much time, so I'm not going to go into the details. But what I'm showing here is that you can use sequential or parallel algorithms to sort your data into these spatial bins. Once you sort them into bins, then you're home free. You can actually do your computation very fast. However, there are two problems with these bins. One is with non-uniform data, the bin size that you need is not going to be uniform. But most of the current binning techniques use uniform bin sizes. So you will end up usually end up with bin sizes that are too small or bin sizes are too big. And so what we ended up doing with this particular class of application is we started to produce what we call the compact binning techniques. We actually just sort all the data and put a cap on the biggest bin that we were willing to produce. And then all the bins that have fewer data will actually not be allocated space. So this requires us to do a two-pass approach. Scan through the data and figure out how many elements will go into each bin. And then we go through a second pass. that actually take the data and put them into either bins or into a separate pool called what we call the sequential pool. And then we will use the CPU to handle the sequential pool. If you look at all the high-performance sparse matrix solvers, they use essentially the same form, what they call the ELL format and the COO format, for exactly the same reason. Okay. So with this approach, you will end up with variable size bins on the left-hand side, and then the sequential bin on the right-hand side. And then we will need to be able to determine the start and end of the bins because it's variable size. So then we use the size information and do a prefix scanning. And this has turned out to be one of the issues that we have eating into the performance of a scalable algorithm, because we need to do the extra scanning path to be able to regularize our data. And then we do the actual binning. So this particular data distribution is one of the worst distributions that you can generate with MRI today. We are using a particular compressed sensing technique that gives us more than 1 million data samples in a very small area, and then much, much sparser sample outside. And that creates a very large sequential bin, or a very large wasted area in this loading balance on the GPU. So what we currently get is about 2 to 3 times faster for the than the best sequential code for this data distribution. However, if you make your data just slightly more uniform, then suddenly your speed up can go up to 10s and then 20s and so on. You can just see that speed up going up very quickly. The same problem exists in graph algorithms. For shortest path algorithms, or the breadth first search problems, if you have free-form graphs, you can actually end up with slower execution than sequential execution. So I really think that a lot of the engineering problems are going to be in how we handle these kind of things in the moving forward. So let me begin to wrap up. What I hope that I have done is to take you through some very seemingly simple computation, and then show you why a truly scalable parallel implementation of these computation is a fairly complex and demanding engineering problem. And that's the reason why we have not trained our programmers to really deal with scalable parallel programming. So obviously, there are several opportunities in this, in this domain. The first one is building programming tools. Everyone has been talking about programming tools to facilitate these key, engineering techniques. And I'd like to, go back and then, cite one particular, statement that Dijkstra had. He said programmers should write code for others to understand instead of for computers to execute. And today, what we end up doing after we finish all those engineering processes on our source code, the code is truly for the computer to execute, not for humans to read. Okay, so we need to figure out how to remove some of those things from the source code. Without tools, we won't be able to do it. And we also need to be able to have performance portability tools. One of the things that we are seeing is for every ISV that actually produce OpenCL or CUDA code, we see that the code actually needs to be re-engineered for each platform today. And that's not an acceptable situation. The tools should at least eliminate the need for producing multiple versions of source code and having people to go through the same engineering process multiple times. The second one is, I think, even more prevalent. That is, regardless how good the tools are, the programmers really need to understand the engineering process. And we need to establish programming as an engineering process into the future. So we need to develop new algorithm techniques. We need to have combinations of expertise in our students in terms of machine organization and numerical methods. And we need to have well-characterized algorithm components. I still remember in the old days when I was an undergrad student, I was a EE student, there were so many good TTL parts with well-characterized speed and power and so on, but not for software algorithms, right? Currently, we don't have any of those kind of characterization for our algorithms and libraries. Data arrangement techniques, we really need to begin to have more disciplined way of managing data. So having said that, I actually think that computer engineering programs are well positioned to produce the next generation programmers, but I think we need to make some changes. The first change I see is that we need to really teach programming as an engineering discipline. We need to have systematic algorithm engineering. The order of magnitude complexity analysis is a good thing, it's a very good thing, but it's not sufficient. Okay, so we need to begin to teach even more of the engineering mindset and characterization of these algorithms. The second one is we need to begin to develop the data engineering discipline, layout, locality, compaction, how we formalize these things, how we can train the programmers to use it. And then back to what David was saying in terms of computational thinking skills. We need to begin to inject more of the domain knowledge into our students so that they can actually begin to revolutionize some of the ways that people actually solve their problems or formulate their problems. We need to have students to be able to understand the strengths and limitation of the computation devices and then apply them into the problem formulation so that they can steer away from some of the limitations. And so that pretty much concludes what I want to say. But I do want to say that Technion is one of the most reputable technical schools in the world. In fact, every year when we look at our grad school applications, we always look for Technion students. So so there's something a little bit selfish here because I would love to have you to evolve your computer engineering program so that we would love to come and hire all your undergraduate students, and all the companies will hire all your grad students. Thank you.